All right, we left off on looking at the exponential function and the log function. And we want the log function with the exponential function put inside to produce z. Then we also want the exponential function when put in, with the log put inside of it to produce z back as well. Now, writing the logarithm as some presumed mu of xy plus a nu of xy I, and we put it into this equation, then the exponential of the logarithm of z will be the exponential of mu plus nu I. Now, the exponential function distributes addition to multiplication. And the exponential function, we've said, when only a real number is going to go in, is going to be the e to the u. And when we just have this complex, we have e to the I nu. And so this is some r e to the I phi, some angle. Now, if we want this answer to be our original z, and so if we set our original z as little r e to the I theta, well then, in order for these two to be equal, capital R has to be little r, and theta plus any multiple of 2 pi can be phi, because the cyclicity of the cosine and sine function by 2 pi, and any multiple goes there. So we have lots of choices for how v is going to work in the logarithm function, so we get back r e to the I theta, because that 2 pi k cyclicity of cosine and sine will produce the same answer. Now, when z is written in the form of r equals e to the I theta, that means r is actually the length of z. So now let's look at this expression. This e to the u is supposed to produce r, which is the length of z, and it's pretty clear there's one choice, an obvious choice for u, is that u can be the log of the length of z. E to the log of length of z will produce length of z back. So here we go. We've got several choices for writing down a logarithm. Our logarithm can be defined as ln of the length of z plus an angle. We're going to call it the argument of z. So anytime you write z in polar form, there is some angle, there's some length, and there's your z. And if we define the argument in such a way that you only use numbers from minus pi to pi, so all the way to there along this line and all the way back. So we're going to pick one. If we pick this one, that's called the principal logarithm. Now, if you decide to say all angles are from pi halves to minus 3 pi halves, you have a different defined argument. So I could call argument prime of z an angle where it's from minus 3 pi halves to pi halves. That would be a silly way to do your polar, but you make a choice. All right, so we made a choice for this logarithm, so there's one answer here. Now let's observe that it truly extends the real logarithm. So if we put in a real number into this one, that's r plus 0i, well, it's the log of the absolute value of the real number plus, and the argument of the reals is over here is 0. And so it'll be the log of the absolute value of the real number. Now that's really nice. We do have some problems, though. We don't like negative r's to be put in here. They would be allowed by this formula, but it presents a problem. So for the time being, and we'll explain why in a little bit here, we're going to take the complex plane and we're going to eliminate the negative real line and 0, 0. So it's okay. All of these numbers we're going to put in there, and we're going to declare that to be the domain of our logarithm. Now, every time we put in a real number, the log of the real number is just the absolute value of the real number. It works just fine, and we're not going to put in negatives for the time being. So let's do some calculations. what's the log of 1 plus I? Well, that's here. So its angle to there is pi fourths. 1 plus I, its length is root 2, so we get log root 2 plus pi fourths. There we go. Let's do log of I. Oops. Always use a capital L so we know it's the complex one. And that it's the principal one where we choose our angles defined in the polar way in a very specific way. Now this would be the log of 1 plus angle will be pi halves, but the log of 1 is 0. By the way, these are positive, so I didn't write the absolute values. So they work out pretty nice. Now, let's check to see if things are working right. With this definition, let's calculate the exponential and the logarithm and make sure we did everything right. So the exponential of the logarithm of z, well, this is the exponential of the ln of z plus the argument of z. Ooh, I forgot to write the I there. Let's back up to all of these. There was supposed to be an I written there. Typographical error throughout that whole thing. Bad, bad, bad. All right. So now, when this is plugged in, this is the exponential of the ln, the length of z, exponential of arg of zi, which this is going to be the length of z times exponential of I theta is always going to be cosine theta plus I sine of theta. And so this will be r times, so this is the cosine of some angle that defines z, plus I, the sine of some angle that defines e. And lo and behold, that's just the polar form of what we started, z. So, formula checks. Now let's do it the other way. The log of the exponential of z. Well, the log of the exponential of z needs to be applied to this guy. So let's write the exponential as an e to the x plus yi, which will be an e to the x times e to the yi. Now that's the real, that's the r, and that's the polar part. And so we get the log, the ln of the absolute value of e to the x, which is already positive, which would be ln e to the x will be x, plus, and now we're going to get the log is the argument of e to the yi. Now, if y is too big, then this argument of y isn't between minus pi and pi. So we have to choose the argument of this to be undone. And so it's going to work. This will be yi only if y is in from minus pi to pi. Now, we also threw away those angles that we probably don't want to work on, but these are going into the exponential. And so we won't get these answers out here. This will be open. Now, that presents a problem. It says that the logarithm will undo a specific piece of the exponential function, an exponential function in this range. So let's draw a picture of it. So the part of the exponential function that the logarithm is undoing, and remember we talked about the domain of the exponential function has to be right. Well, this region is the region of the exponential function that the logarithm will invert. And if you remember, we also proved vertically that the exponential function in the complex plane was periodic vertically in a period of 2 pi I. So we're only going pi up and pi down, and we're not going to touch these edges. So that is going to be the 1, 1 region of the exponential function that the logarithm will invert, and this is the domain of the logarithm function. So when we restrict our exponential function to this region and use the logarithm, principal logarithm in this one, these are the domains in which the exponential and logarithm properly invert each other. All right. So now that we've discovered why we work so very hard at defining this, do you think all of the old properties of logarithms that we learned in reals are still properties of logarithms in the complex plane? I mean, here's one law. The log of an x, y in the reals is supposed to be the ln of x plus the ln of y. Could that work? And how about this one? The ln of an a to the b should be a b ln of a. And the ln of x over y should be ln of x minus ln of y. We have all these neat properties. It'd be kind of nice if these actually were properties that worked in the complex plane. Now, there is a problem. First off, this guy right here, we haven't done yet. For example, I raised to the 2i. What's that going to be equal to? We haven't done the complete algebra of the complex plane. The other thing is, it turns out that, well, these two have problems. They have problems because of our choice on the periodicity associated with the argument choice for the logarithm. And because you're going to be adding arguments, look at this problem. Suppose you have a log of some complex number, and you're going to add it to a log of another complex number. This is going to involve, by definition, a real number and an argument of the z-naught. And this is going to involve, by definition, a real number and the argument of z1. And guess what? If these two angles are large enough, then the sum of the two angles will be beyond the allowed range of an answer for logarithm. The logarithm, anytime you have a logarithm of a single number, you're going to get a real number, ln of something. We could make this a real number. Clearly, it's log z0 times z1. That would work. But when these two are large enough, it's not going to be the argument of something. It will get too large. So let's do an example. All we need example of failure of log x times y equals log x plus log y. These x and y's are complex numbers. Well, we just need to find 2. And in order to find 2, we just need to have 2 numbers whose angles are sufficient so when they add up, there's trouble. So here we go. Let's do the log of I, which will be ln, the length of I, and the argument of I will be pi over 2i. And let's do the log of, I think they do I minus 1. Minus 1i, and notice that's going to have a big angle. And so this will be log square root of 2 plus, and the angle will be, what, 3 pi fourths? And now if we do the log of I times I minus 1, which is the log of minus 1 minus I, which will be ln the length, the square root of 2, but the angle will be minus 3 pi, minus 3 pi fourths I. And these two added together don't equal this. And that's the problem. And so this principle of choosing the argument in a specific way with that periodicity, we're not doing modular, we're not doing cosines of an angle so that they go away. They're still present, so the numbers aren't correct. So this logarithm looks nice. We've just had a failure, though, of one property. That property, of course, though, does hold on the real line because the arguments don't come into play. All of the arguments are 0. So what about this? Let's do calculus now. So let's take the logarithm as we've defined it with this argument of zi and ask what is its derivative. Now, if we've done things right, its derivative should be, answer, 1 over z. Well, if the derivative exists, we know we can use Cauchy-Riemann equations to do this. And this is set up for Cauchy-Riemann equations. Well, the answer, if it's correct, if right, it's going to be the partial of this with respect to the x coordinate. So, okay, so now, is it possible that with this nice definition, that we could possibly have this wonderful fact? That not only have we extended the logarithm to the complex plane, have we extended differential calculus to have this neat result? Well, if it's going to work, we should be able to use Cauchy-Riemann equations. And this is absolutely perfectly set up for Cauchy-Riemann equations. So we begin, and we're going to say, well, this will be the answer by taking the partial with respect to x. Log absolute value of z plus arg zi. Partial of the sum of the partials, now, absolute value, or the modulus of z, it's not a hard concept. It is the square root of x squared plus y squared when we set z equal to x plus yi. Now, its derivative, first I'll put the 1/2 in front, property of real logarithms, and the partial of that will then be 1 over the x squared plus y squared times the derivative inside, which will be a 2x, and that'll cancel. So that part's pretty simple. Now, the argument of a complex number. Well, we put the complex number in the plane someplace, and we get its angle theta. Well, theta, this is from Calc 2, is the arctan of y over x. So what is the partial with respect to x of the arctan of y over x? Well, the derivative of arctangent is 1 over 1 plus the y over x squared times the derivative of the inside, which would be minus 1 over x squared with the y, and we'll have an I. Now, this looks slightly onerous, but it's actually not, because this reads x over x squared plus y squared plus minus yi over x squared plus y squared over x squared, which reads x minus yi over x squared plus y squared. And guess what happens when you multiply top and bottom by the conjugate? You get x squared plus y squared over x squared plus y squared. And the conjugate that went into the bottom was x plus yi. These cancel, and lo and behold, you get 1 over z. Oh my goodness. this is working just wonderfully. Now, please notice, when I used arctangent is actually the inverse of the tangent function on the principal part from minus pi halves to pi halves, which means that it fits into the argument principle here just fine. All right. So its derivative is nice. Please notice in the book that they have an alternate proof by using inverse function theory, that the derivative of a function is the derivative of its inverse with another value plugged inside of it that made this happen. And this turns out to be 1 over z. There's a little bit of an argument how you get to that, but that's okay. All right, so logarithms seem to be working nice. We are almost ready to get to the point where I was not using e very often for this exponential of z, because it turns out I never defined an a to the b. We defined an e to power, and we made sure that it made sense. But now comes the fact is, why is the exponential actually using e? So we're going to look at how to define complex number to a complex number. Now, you shouldn't be surprised when you see this, because complex number raised to a complex number, we're going to emulate what we did with the reals. Do you guys remember the square root of 2x raised to the cosine of x, and somebody asked you to do a derivative? How did you figure that out? Well, the answer was you usually did this. You did e to the ln, the square root of 2x, raised to the cosine of x. Then you used a logarithm property and then you did some simplifications. And there's some constant here because of the plus c. And now you took the derivative of this. But lo and behold, this is just a product rule. So guess what? The derivative of this is doable when you believe in exponentials and logarithms. So it also taught us that this is a way to define a to the b right here. Let's do that in the complex plane. Let's do a definition. That z0 raised to the z1, z0 and z1 elements of the complexes, we want to define it to be, well, the exponential of, and we're just going to put the z1 right away in front, times the log of z0. That is going to be our definition. Now, with that definition, we can now do complex values. Now it actually makes sense for us to talk about legitimately what this function would then mean. We define this basic exponential function in the background, and now if we actually do limits and we discover how the value e comes into play, then we can discover this e to the z makes sense within this context, and everything is consistent. That makes our world a very doable world. All right.